Hello everyone, welcome back to another Sunday video. In today's video, I'll be continuing the Traces series. So this is part 3 of Traces, of decoding traces data on EVMs. If you have not watched part 1 and part 2, highly recommended to get you up to speed with the basics and also watching me going through decoding traces for Blur v2 in part 2. So this part 3, I thought I want to do another example of how you would go about decoding traces. And I've got an example here on Astaria, which is a protocol on Base that lets anyone borrow any or collateralize any ERC20 and ERC20 and NFTs using something called an intent feed. So anyways, before we begin, maybe just a refresher to decoding. Well, when we actually do the decoding, we just need a few things. One is, of course, our handy dandy regex. This is not needed to pull out the input, and then cut it up into lengths of 64 characters, and so that it's all in this array and it's easier to work with. The other thing to know is that there'll only be a few important data types: address and unsigned integer, or I guess there's also signed integer, but we'll just use these two. For address, the usual treatment is substring, right? You cut off the segmented, let's say it's the first object, right? And then you start from the 25th character, cut off till 40 characters long, and then you add AOX in the middle. Right, this is the regular treatment for address types. And then for integer types, it is usually utils.udf hex to int. So converting hex data to integer. So again, looks something like this, right? And in this walkthrough, I will not be doing this, right? I will not be manually converting this. Maybe I will. We'll see how. But the main reason for this walkthrough is I'll just talk verbally on how to decode it, basically. And another refresher for traces is that when you're dealing with traces, there will be something called offsets, which is how many bytes or lines, right, quote lines, to skip. And the lines have a hierarchy, right? Yeah. and then when you're dealing with arrays, there will be array length indicator, right? Array size, I should say size. Sure. And then there will be yeah, I think that's it, right? Just offsets and array size, and then of course there are positions, which is literally just means offsets again. So yeah, there are some rules to apply when it comes to traces. If you're not sure what these are, again, watch part 2. These are all covered in part 2. Alright. Alright, that's a quick water break. Let's begin. So I have this transaction over here on Base. Shout out to Joel for sending me this transaction. It is a transaction on Astaria where someone accepts the loan offer, where they accept the collateral of 100,000 USDC to borrow 60,000 or 60 billion mock coins. And it is we'll just try to decode this. If you look at the logs, you would see that there is actually an event which is called open, and it is not decoded on base scan. But if you look at our decoded event logs table, this is decoded. So maybe let's just start off with that. So select all from base.car.fetch where block timestamp date is. What is the timestamp? August 21st. So August 21st and transaction hashes. Let's just see what information we can get from the event logs table. It should be this one over here, open. So, oops. Yeah, looks like a lot of things are available, right? You've got loan, borrower, all the collateral information, all the debt information, all the terms as well. So it is very complete, I would say. So there is no reason to use traces or decode traces manually here. But why not, right? In this case, I just want to use it as an example to decode the trace. Alright, cool. So what I like to do first is paste my transaction on blocksec, aka Falcon. And if your chain does not have blocksec, or blocksec does not cover the chain that you're looking for, that is totally fine. What I just want to find out is whether or not this is a delegate call, right? A delegate call is when the contract makes a call to another contract which houses all the functions. So it's something like if your contract wants to, the contract itself doesn't store the functions, it relies on other contracts for the functions. So in this case, there are no delegate calls, and so I can just use this trace directly. So if you do not have blocksec, what you can do is you just use the traces table and check if this contract, the contract that the user interacted with, did they do a delegate call to another contract? Yeah, that's basically it. In this case, I just use Falcon to see. I can see there are none, so I can just use this trace directly. So let's see what the traces table looks like. Okay, so again, first thing I like to do is I like to filter by trace index ascending order, so I can see the in ascending order. So yeah, this is the user, and this is the contract that the user interacted with, and you want to check if this contract from the from address, this contract in the from address column, whether it made any delegate calls. It did not, right? It's all static calls, August calls, which means this the function itself is housed within this contract. So that which means we can just use this specific row. So I can just say and to address is this, right? And then my function would be the first 10 characters of input. So left input 10 is this. Set 10, 2, 4, 6, 8, 10. Okay. So by using this filter, it assures that I am only looking at this specific function on this address. Okay, and what I usually do is I have this regex. Yeah, I think that's pretty much it. Normally you have like transaction hash, right, trace index, but in this case I just want to get this. Okay, so let's go ahead and copy this. How do I copy this? Does that work? Then go on to my another favorite site, the JSON beautifier sites. So this would be my tab for the input data, right? The raw input data that we're going to decode. Next step, because there are no there are no implementation contracts used, which means there are no delegate calls being made to another contract. I'm gonna go ahead and find the contract, which is this star port, and head over to the contract tab, scroll all the way down to ABI, copy this, open another tab of JSON viewer, oops, and then oops, oh, looks like I did not copy that right. Where is the ABI page? Oh, copy. Alright, there you go. So the right side would be my ABI and the left side is my data that I want to decode. And let's try to find what function, right? The function here is called originate. Now you can of course figure out the function's nature manually, but that is a lot of work, and I'm just gonna use from here directly. Yeah, originate. So search for originate, and you want to make sure that it is a function, so type function. So this is exactly what we're looking for, which is the 71st item over here. So scroll up and let's take a look at this. So it has no outputs, okay, it has 4 inputs, and all 4 inputs look very nasty. I'm just gonna do like this so you can see all the components all at once. So all of these are tuples, which just means a collection of different data types. And then this bracket over here indicates that there are multiple collections of additional transfers. So if this is non-null, then there are more rules to be applied here. Yeah, more offsets to go over. Alright, so let's start. Before I begin, again, water break. Very important to hydrate, guys. Alright, let's begin. Okay, so because there are 4 I guess 4 inputs, right? There will be 4 offsets in the first thing you see, and which is what you're seeing here, right? So the first line refers to the first offset, or the offset for the first object in inputs, which is this whole thing called additional transfers. The second line would be the offset for this next thing, which is called borrower caveat, right? And we'll get into the specifics each component in later on after the initial offset. So another website that is useful is the hex to integer conversion. Essentially, all these are integers. In its hex value, and you convert them into integers, and this represents the amount of bytes that you need to skip. And because one line or 64 characters has 32 bytes, so you just need to divide by 32. So this tells us I need to skip 4 lines before the start of additional transfers. So 1, 2, 3, 4, skip, right? All this skip. The next line would be the start of additional transfers. And lucky for us, this is 0. And in my experience, this just means it is null. So there are no additional transfers. Let's just double check that. Yeah, okay, so it is null. So we can happily ignore this whole bit. Okay, cool, so that's done. The second line would then tell us the offset for, again, the second object, which is borrower caveat. So convert this, 160 divided by 32 is 5. Okay, 5. Yeah, so 5. So because this belongs to the same category or same hierarchy, I don't know what's a more suitable term, but because all these 4 inputs belong in the same hierarchy, they start from the start of the hierarchy. So we should be here. So 1, 2, 3, 4, 5. 5 lines to skip. The next line is where we will start. So the next line, let's look at what the next line is. The next line is the start of borrower caveat. And inside borrower caveat, there are 5 components. Yeah, it's a boolean, it's an integer, some bytes, and then some arrays. Not array, but address type, and then bytes again, and then we close it off with a bytes of signature. Okay, so let's see. So the first one is boolean, which means this is a boolean, and 1 this means true. 0 means false, if I'm not wrong. Yeah, I think that's right. 1 means true, 0 means false. So yeah, single use, true, right? So I will not be actually like writing it down here. Right? You can do it by your own, but I'm just gonna verbally decode it. Single use in this case, boolean is true. The next line would be deadline. So it's an integer type. So again, you convert this to an integer, which will give you this, and you need to apply the 2 timestamp. So timestamp convert to uint, then use to timestamp. Right, so the 2 timestamp function on Snowflake converts the integer to a UTC timestamp. Cool, that's done. Next, moving on, it's salt, which is 32 bytes. So which means this whole line is the salt. That's it, done. Next, we encounter a tuple, which means there can be multiple of this collection, which means it can be enforcer data and then another enforcer data, right? So it depends how many number of collection there are over here. So in this case, there's an offset. So we convert this to 160 is 5. So, and because this is belongs to this hierarchy of input 1, which is borrow caveat, we start from input 1. So single use is that boolean over here. So 1, 2, 3, 4, 5. Skip. Start at the next one. So this is the next. This is the start of caveats. And because it is an array, noted by this, the next time will tell you how many. The next one will tell you the array size. In this case, if you convert this to integer, it's 1. Okay, and yeah, basically you convert this to integer, it's 1, which means the next line is, what the hell is this? Let's see, 32. Okay, so this is the offset. Again, so this tells you there's only one object in the array. The next line then tells you the position of the first object, and it tells you by telling you the offset. And because there's only offset of 1, right, this one gives you 32. 32 divided by 32 is 1. So that means the next line would then be the caveat. So in this case, it first is an enforcer address. So this is address type. And let's see where we are. So we started here. Salt byte. So salt is here, and then we started here where we skipped 5, right? And then 1, 2, 3. Oh, sorry. 1, 2, 3, 4, 5, and then this is the 1, and then 2 is this. Okay, then the next thing after this would be this, and this is the offset for bytes, if I'm not mistaken. Let's see. It should be. This would be 50. So, oh my goodness, I have to count 50. Alright, YOLO, I guess. Let's see. So it begins. It begins here. If offset is 1, so it's plus 1. So 50 would be 55. So 55 is 41. So yeah, I believe this would be the signature. Sorry, data, right? Which is bytes. So I believe this is it tells you uh, the size of the bytes, if I'm not mistaken, which is 65, which means there will be 65 times 2, 130 characters long. Yeah, so maybe it's something like this. This is 64. This is 64, so 128, 128 plus 2 is 130. Perfect. So yeah, 55 is the data. And yeah, because it's bytes, it first tells you the length of the byte, and then the length of the byte, one byte has two characters long, and so 65 times 2 is 130, and 130 is these two lines plus 2 characters here. So that is bytes. Done. Alright, let's scroll up and find where we left off. I believe it is here. Alright, this is the byte. This is the data, and then this was the array size for enforcer, and then this was the offset for enforcer. This is the address for enforcer. Now the next line would then be, I think we're done with this. So the next line will be the fourth, which is again bytes. Let's convert this to 64. So skip 2. Skip 2 is interesting. Or does this mean the length of the bytes? Signature bytes. I mean, this should be the length. So 64 times 2, 128. Yeah, it should be these two. But all this bunch of zeros, 500, and then a bunch of zeros, 20. So let's double check with Falcon to see if that indeed is the signature. So let's see. Borrower caveat, which is what we're looking at. Caveats data, which is what we just saw on index 55, right? Array. Signature, it is this 0x4a5e. Okay, so that means this is not the length. I mean, this is not the signature over here. It must be somewhere down here. I mean, yeah, I can see this shit is confusing. Yeah, there you go. Hey, wait, I've already decoded this signature. Wait, what? Caveats data. What is data then? Oh wow, what the hell is this? 0x00266c. Oh, is this it? Yeah, it looks like it is 2DA. It ends with 120. Interesting. Okay. So it looks like what we found on 55 is actually the signature and not data, which means I forgot something somewhere. Let's see. So okay, so this is enforcer. No, this is not enforcer. Who is the enforcer? A6F. A6, okay, it is the enforcer. So this part is right. And then the next part is, okay. Okay, so my bad. So from here, after we've decoded the enforcer, which is address type, we should immediately move on to the next bit, which is data. And in this case, because data is bytes, yeah, I've no idea about this part, but it seems like the bytes starts from here all the way to I don't know where. But earlier when we did the offset for number 9 over here, it is actually for signature, right? Which is the one that we found with the 130 characters long bytes. Alright, cool. Yeah. I think that's it for borrow caveat. See, it's probably wise if I have some sort of a notation tool here where I can just like note down where is where. But you know, YOLO, let's go. Lender caveat. Tuple. So let's cheat a bit here, and let's cheat by looking at where the signature ends. Sorry, where the data ends. It ends with a bunch of 12. Yeah, I think it ends here. 55. Yeah, it ends here. And then 55 was my bytes. So this again, this indicates the length of the bytes. We did this earlier, right? This amounted to what was it, 64? And then 64 times, no wait, what was this? 65, sorry. 65 times 2 is 130, and then 130 ends here. And then because it's a bytes, all of this will be padded, so you have a bunch of zeros. Yeah, okay. So what is exactly lender caveat? Is it just a bunch of zeros? Let's see. Yeah, it looks like it is. So it says here single use false and deadline 0. So which is why we're seeing 0 here. So single use is this, deadline is this. Alright, single use deadline salt 32 bytes. There's no salt. And then enforcer and that one. This would be the offset for enforcer. So 60. This is 5. 5 from single use. Oh god. 5 from single use. I believe this is one. So 1, 2, 3, 4, 5. Skip. And we start from this one. It's 0. So enforcer is 0. Nani? Wait, what am I looking at? Okay, lender caveat, that's right. After deadline and salt. After deadline and salt, caveat is 0? Oh, okay. I mean, that explains why I'm seeing 0 here, but I didn't know that even if it's null, they still show the offset. That is interesting. And after enforcer is data. So bytes format 32. So 1 offset to skip, which is this one over here. Yeah, it's 0, which is why there's no caveat at all. And then after caveat is signatures, and again signatures is 0. Okay, there's a bunch of zeros here. But okay, so signatures 0. So this whole lender caveat thing yeah, this lender caveat thing is just a bunch of null, so there are no lender caveat, I'm assuming. And then last but not least, we are looking at a loan tuple. So let's see what it says. First is a integer, so this would be this an integer? Doesn't look like an integer. Looks like an address. I'm assuming this is the integer, so let's double check. Yeah, it is the integer, was start 0. So I must have missed out a 0 here, which means the end of lender caveat is this one, and this is the start of loan. Yeah, this is the start of loan. And the first thing in loan is an integer, so this convert to integer is 0. The next is an address, and yeah, this looks like an address, right? You can just substring cut off the bunch of zeros in the beginning, and then this would be your address and then add an OX in front. Next is another address, so this is straightforward. This is another address, borrower address. This is the issuer address, so this is the issuer address. Originator address would be the null address, so a bunch of zeros. And now there is a tuple, like array, is collection. So again, there will be offsets. This would be 256 divided by 32. How much is that? 8. So I need to offset 8. 8 starts from the 0 over here, which is this. So 1, 2, 3, 4, 5, 6, 7, 8. Skip, and this is the start of, what is it? The start of this component over here called collateral. And it tells us, I think this is one array, or it could be the start of this thing itself, right? So it could be item type. I'm just guessing here, but I think it is the item type directly, so I can just use this. So item type 1, and then the next one being token address type. This does not look like an address type, so which tells me this is this tells me the array size. In this case, the array size will be 1, and the next line is actually then the start of the collateral. And the start of collateral, the first item is item type, so this is item type, which is not this, right? So this is the item type beginning. So item type 1, and then token address would be the next one. So this is the address of the token, 833. So let's double check that. What is 833? The mock token is 833? No. Oh, I see. USDC token on base is 833. Couldn't recognize that. So used to the address on ETH. Alright, so this is the token address. The next is the identifier 0. And the next is amount. So the next is amount. Yeah. So let's convert this from hex to in. You get the amount of USDC in its raw format. Another thing to note here is that it looks like they're using item type and identifier in this sequence. In this combination of item type, identifier, token, and amount. This feels like, if you guys know OpenC, its contract C port also uses this exact same thing, where item type is, I guess, item type, right? Item type 0 means ETH. Item type 1 is ERC20, item type 2 is 7 to 1, item type 3 is 1155, and then there are other item types which are like ERC 7 to 1 with consideration or something like that. And then identifier is the token ID. So in this case, because it is item type 1, it is a ERC20 and it does not have an identifier. So identifier is 0 here, and then this is the amount. And I think that's it. What else did we look at? Oh, Oh yeah, that's it for the collateral section. There is still the debt section, which should be the following one. I am guessing that again this is the array size or array length, and up here somewhere, I forgot where, but up here somewhere would tell us the offset. We should, if we count the offset, yeah, it's this one up here. If we count the offset, it will just end up here. So here would be the array size, which is 1. So it means the next line will be the start of the first array, and in this case there's only one array. The first item is then item type. So again, the same thing, item type, token address, identifier, amount. So convert this to amount. We get the amount of mock token. So this would be 60 billion. Yeah, or trillion or billion. 60 billion mock tokens. Oh, where was I? Yeah, item type 1, token address, identifier is 0, and then this is the amount. Yeah, okay, cool. So that's all for that because there's only one array. If there are multiple arrays, the next line will be the start of the second object in the array. Alright, let's see number 7. Number 7 is something called terms, and terms starts with an address of status. So this is an address 2546. Let's double check status 2546. Yeah, there you go. So this is an address type. The next is a bytes status data. So this would tell you the length of bytes. So convert 192. 192 times 2 is 384 characters long, divided by 60. Oops. 64. 6 lines. So 6 lines of bytes. Oh boy. 1, 2, 3, 4, 5, 6. So these are the 6 lines of bytes. The next is pricing address. Did I count wrongly? 1, 2, 3, 4, 5, 6. Let me count again. 192. 192 times 2 is 384. 384 divided by 64 characters is 6 lines. Yeah, I think that should be it. I'm imagining things. Status data. Interesting. Looks like there's an offset here that is not accounted for. Unless this is the offset. I mean, 192 divided by 32 is 6. So it might be the offset. But I don't know why. So, but you will count the offsets from your status, which is the one before address. Yeah, so 1, 2, 3, 4, 5, 6. The next line is the start of your bytes, which is in line with what we're seeing here. Yeah, for some reason, this is an offset. I have no idea why. 96 times 2 divided by 64, 3. So 3 lines. So it should be 1, 2, 3, I assume. It ends with 80,000, is it? Okay, cool. It ends with 80,000. Okay. So we figured that part out. This is bytes from status data. Pricing is the next one, so we need to go back to the offset before we skipped. The offset is here. So this would be pricing as an address type. So let's check 95 BCF pricing. 95 BCF. So there you go. So that's how we continue back after we do the offset stuff. Okay, so pricing data bytes, another bytes. I'm sick of these bytes. 320. So 320 is 10. So what's our start? Start is status. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Skip. The next one will be the byte size. Byte size is 96 times 192 divided by 64 is 3 lines long. So 1, 2, 3 is bytes. What was it? Pricing data. So pricing data ends with 12. Let's double check. Pricing data ends with 12. There you go. So yeah, these 3 things is pricing data. Alright, let's next one is settlement address. So oh God, where was it? Here 95 is our pricing, and then this is the bytes, and then this is the settlement address, and this is the settlement data. And other bytes do the same thing, where you times convert this to hex. This tells you the offsets you need to account for. 14 lines. Skip the 14 lines beginning from status, which is this one. This one. And then skip 14 lines. The next line would be the length of the bytes. First, you need to convert it into integer times 2. Right, all those things, and I think that's it. That would tell you the rest of the data, and all 100 objects in this array would have been accounted for. God, that was long. Hopefully not too long. If you're still watching this, thank you for watching, and let me know in the comments if you're still here. But yeah, I think that's it. Hopefully you learn a thing or two, get some practice on how traces data is decoded manually. There are some parts in there where I wasn't sure, right? Because it's sometimes a game of like guessing almost. But in general, that's how you do it. Okay, and yeah, these are the common things that you normally need. Alright, that's it from me. Thanks for watching, and I'll see you in the next one. Bye.